Okay, any questions on stuff we're doing? Let's go ahead and do, so what we're going to do is we're going to move now, we're going to transition from thinking about molecules and pictures of molecules and shapes of molecules, mostly. I'm going to do a practice problem first, but we're going to transition from that to talking about chemical reactions. So now everything's going to become letters, all right? There were letters with electrons. Now they're going to just, and bonds. Now they're just going to be letters on a whole bunch of the stuff we do in terms of chemistry. So we're going to talk today about drawing equations, balancing equations. We've done some of this before, but now we're going to get into it in earnest. But what I want you to do is I want you to still try to think about these things as molecules or as atoms. And so what I mean is little spheres, okay, little spheres running around, bumping into each other, trading partners, all sorts of things like that. Okay, that will, if you can think about it and imagine them like that, that's going to be a good thing, and that's going to help you keep chemistry less abstract, okay? While some of chemistry is quantum mechanics, which is very non-intuitive, this sort of picture is fairly intuitive, right? We're used to balls and things like that in our lives. So if I think about water, my colors are all wrong for the model or the atoms I have in my class, but I think about this, okay? I'm going to go ahead and pass that around, and but I want you to think about these atoms and these molecules like that, okay, not as letters. Okay, so let's go. I had somebody come ask for help yesterday in terms of this polarity concept, and so I'd like to do another problem with polarity in here and just talk about it. I know that it's a difficult concept. We also have the molecular orbital theory stuff that was on your last homework as well. That's even less less intuitive. I'm not going to emphasize that as much as polarity. So we're going to go ahead and do a polarity problem, and then we'll move on. In terms of the molecular orbital theory, I didn't look at your labs. Did you guys, those of you that had lab on Monday or Tuesday, did you guys do any MO theory in there? Like where you had the lines and you had to put the electrons and fill it up? Yes, no? Okay, no. Okay. All right, well, perhaps I'll come back and review it a little bit, but I think not today. Let's go ahead, though, and let's think about, is the following molecule polar? So let's do carbon, oxygen, sulfur polar. Okay, let's say that's our molecule. All right, so I'm going to look over at the periodic table, and I'm going to try to decide my center atom. Leftmost atom is carbon, right? Turns out carbon and sulfur have the same electronegativity, so I'm just going to use the leftmost rule. I don't know whether one with sulfur in the middle happens, but carbon's usually in the middle. So remember, we've got a rule that it's either if you look at one of these things and you see the first atom, it's usually a pretty good clue. It's usually the one that's in the center, all right? But also, if you don't have that clue, it should also be the leftmost atom. So I'd use the leftmost atom as my first rule. So carbon, whoops, let's go ahead. I need to first draw, if I'm going to try to figure out if it's polar, I need to first draw a Lewis dot structure, okay? I'm going to go ahead and do the whole process. So carbon, I need to figure out how many valence electrons I have. Carbon, oxygen, sulfur, there's no charge on it, so I just need to worry about my carbon electrons, my oxygen, and my sulfur. Carbon off the periodic table, counting from the left. That's how we figure out how many valence electrons we have. It's got 4, right? Oxygen, how many? 6. And 6. And if we look at sulfur, it's in the same column as oxygen there. So it also has 6, right? Things that are in the same column have the same number of electrons. So that means my number of valence electrons is going to be 16. Okay? So then my process is I've got carbon in the middle. I'm going to make single bonds to the other 2 atoms. This is your book's process for this. I'm then going to go ahead and I'm going to make each atom on the outside, each atom that's not the set of atom, happy in terms of giving it 8 electrons, right? I'm filling up its octet rule. So I've done that now. Now I had 16 electrons to play with. I used 2, 4, 6, 8, 10, 12, 14, 16 electrons. I have no more electrons, okay? But there's a problem here. What's my problem? Carbon only has 4 electrons around it. 2, 4, right? So I need 2 more pairs of electrons on it in some way, either bonds or otherwise. And so what I'm going to do to fix that is I'm going to fix that by bringing these 2 pairs of electrons in and making bonds with them there. You know, it might take you more than one step of playing around to figure this out. But so that's going to give me this, not that, this. Okay, and so I've got that. I could have done a single bond and a triple bond. Okay, I did 2 double bonds because this gives me formal charges of 0 for each, right? This is my best structure. Carbon has, if I do the formal charge count, let's do formal charge on one of these and then I'll just do the other. Let's check sulfur. Okay, sulfur with a double bond here. Sulfur has, remember our formal charge formula is formal charge is equal to number of valence electrons minus number of bonds minus 1/2, or no, actually, just not 1/2, minus number of unshared electrons. Okay, and so if I look at this, sulfur has 6 valence electrons, right? Counting over from the left on the periodic table. The number of bonds I have to sulfur is 2. And the number of unshared electrons is, it's not pairs, is 1, 2, 3, 4. 4 unshared electrons. 6 minus 2 minus 4 equals 0. Formal charge is 0, right? Okay. And then this is going to be 0, and this is also going to be 0. So that's how I know that's the best structure. It's got the lowest number of formal charge. You can't get better than having zeros and everything. All right, so up to here, this is all review of stuff that you had for your test. Actually, we still have some more review. I have to decide the shape, right? Okay, so you can memorize the table. Like I've said to people before, you can memorize the table for the shapes. You're probably not going to worry about it until the final exam at this point, because I'm not going to, well, we're going to have to do polarity for the next quiz, right? And you might need to do polarity for the next exam. So you might have one of these things where you need another shape. So you can memorize the table, or when I was in college, I just thought about how can I put these things as far apart as possible. I've given you the names of these things on the test, right? So if something's far apart as possible, if I hit the middle atom here, what we've got is that's going to be linear. Okay, I can look at the top of my test, what looks like this. That make sense? Okay, and that's because I have 2 things, 2 electron groups, 2 things, 2 atoms on that center atom, and they're going to get as far apart from each other as possible. So this is going to be linear. Now we need to just determine if it's polar. For it to be polar, it has to have 2 things going on, right? It has to have a polar bond. It has to have at least one polar bond, and it has to have, the polar bonds have to be non-symmetric. All right, so let's see. So does it have polar bonds? All right, so let's go back and look at this. We've got a carbon and an oxygen, a carbon and a sulfur. We're going to go back to the previous notes, and we're going to look at the table. I will give you the table on a test or quiz. Okay, so here, this is a table of electronegativities. That carbon and oxygen, the difference between these two is 1, right? Is that a polar bond? Yeah, it's 0.5 or greater. We're going to call that polar. Carbon and sulfur, 2.5 and 2.5. Is that a polar bond? No, okay, because it's 0. So it's 0.4 or less, okay, or less than 0.5. We're not going to, with this table, I guess we could get fractional differences that are smaller than that. So what that means is if I look at this, I'm going to redraw this just down here where I have a little more room. Is if I was to draw my arrows, my electrons are, I've got a polar bond here where my electrons are going towards the oxygen, and then I don't have a polar bond. Is this molecule polar? Yes, because I have an arrow pointing one direction and there's no other arrow anyplace else canceling it. Okay, so it has polar bonds, and our answer over here would be yes. And then, do the polar bonds cancel? And the answer is no. Okay, an example where they would cancel for this is I didn't do carbon dioxide on purpose. I could have done carbon dioxide, right? And in this case, we just determined that carbon and oxygen do have both polar bonds, but they cancel. It's linear. They pull against each other, okay, equally. There's not a side here that is where I have a negative on one side and a positive on another, okay? Which is one way to think about it that will get you through most of them, but sometimes you have negatives on both sides, but you have more negative on one side than the other. Okay, questions? Perhaps a less obvious example of something that is polar, is nonpolar, I should say, is if I was to draw a tetrahedron here, right? Let's do carbon tetrachloride. I don't know whether this still gets used as a dry cleaning solvent or not. It's a nice toxic, fairly reasonably toxic thing. It evaporates off, easy. Oh wait, carbon tetrachloride. No, not carbon tetrachloride, but it's a good solvent for things. It doesn't evaporate so easily. So this is carbon tetrachloride. Does it have, I've drawn the Lewis dot structure. I've actually drawn the shape here. It's tetrahedral. Does it have polar bonds? Let's go back and look at our table, right? Chlorine is 3.0 and carbon is 2.5. Polar bonds or not? Yes, because it's a polar bond because 3.0 minus 2.5 is 0.5, which counts as polar for us. However, these things are all evenly distributed in space, and when I draw my arrows here, all those arrows are the same size, and they're all pointing. For a tetrahedron, you're just going to have to memorize this. I don't know if it's even intuitive for me after 25, 30, 35 years in chemistry, that this shape means that they're all pulling in different directions. It sort of is, but it's a heavy math problem. Does that make sense? So that is nonpolar. Nonpolar arrows cancel. And the arrows represent the polarity. Questions on that? Yes?
So it's nonpolar because they're all pulling like equal distance?
They're all pulling equally. Okay. So if we made these into vector x, y, z vectors, we turn them in their x, y, z components, all those x, y, z components would add up to 0. I don't know if that helps. They're all pulling equally. This one pulls up, and these, the little component of each of, this one's going this way, this one's going this way, and that one's going back. And it's at a fairly steep angle. And if I add up the little x, the z component here for this one and this one and this one, they add up to this one. Does that make sense? Like I said, you may just have to memorize it for tetrahedral. It's not, tetrahedron is a three-dimensional space, not as easy for us to think about. Yeah, Jack.
How do we figure out which way the arrows are pointing? Is it by the 3.0 minus the 2.5?
Yeah, that's a great question. How do we figure out which way the arrows are pointing? So I was rushing us through the 3.0, right? So let's do it. We've got chlorine, right? The chlorine electronegativity is 3.0, and the carbon electronegativity is 2.5. I'm going to subtract the 2.5 from the 3.0, and I'm going to get 0.5, okay? And then the arrow points towards the thing that is more electronegative. All right, so the way you think about this is, whoops, let me draw the arrow the actual way. So if this is our bond here, the way you think about it is you draw the arrow and then we draw this little cross at the side of the arrow, and that's supposed to be like a plus. Okay. I don't care so much that you can draw the arrows. I don't know if it came up in the homework or not. I did take your homework, but I can't remember. But in terms of you drawing the arrows, but the arrows will get used. You'll see the arrows. That makes sense. Okay. Other questions? Let me do one more thing and then see if there are more questions, and then we'll move on. If I took this tetrahedron and instead I put a fluorine on there, so let me go ahead and put a fluorine on. Once again, we're drawing a tetrahedron in 3 dimensions. And I wish I'd had more time and actually put together a tetrahedron for you to play with. Let me see if I have one in here. Okay, I do not. Let's just do let's jump out to that website we had before real quick and look at a tetrahedron. Okay, well that's a tetrahedron. Whoops, I ran into math. Tetrahedral. Let's try that. Here we go. Okay, so here is a tetrahedron. This is a tetrahedral molecule. You see how we've got the atoms there? And then here they don't exactly show the bonds, but they're showing the atoms. You've got your center atom, and you've got your atoms on the outsides there. All right. So let's go back to this. Chlorine. The chlorine-carbon bond we decided was 0.5, right? That's got an electronegativity difference of 0.5. We're calling that polar. I'll go ahead and do these in green. So I'm going to draw some lines like this. All right, and then the chlorine-fluorine bond. What's the electronegativity of fluorine? Well, it's 4, but we can look at it on the table, right? So the difference between 4 and 2.5 is 1.5, right? 3 times as much. And so I would draw this arrow 3 times as large, to the best of my artistic ability. And this one is polar. All right, so the arrows are pointing in the directions that they could cancel, but this arrow is a lot bigger. So this is a polar molecule. Does that make sense? Another way of saying it's polar is the molecule has a dipole. In other words, it has a side that's positive and a side that's more negative. Okay, so the way this would be is this would be really negative over here, and then we probably have some small negatives here, and then we have it has a net movement, has a net negative over here, some small negatives over here, but they wouldn't cancel that out. Yes?
Wait, what did you say the difference was for carbon and fluorine?
Carbon and fluorine would be 1.5.
What did you say was for carbon?
Carbon chlorine is 0.5. So this and that. Okay, and I'm just pulling those and subtracting the differences off the periodic table. And you never talk about those differences being negative. Okay, just make sure you point the arrow at the more electronegative atom. Okay, but I'm not going to ask you to draw arrows, but the arrows might help you in figuring it out. Other questions? Good questions. Thanks for them. Okay. Remember, if you have a question, don't be shy. Probably 4 or 5 other people have the same question. All right, so we're going to move on and we're going to talk about chemical equations then. So probably, especially since I spent a bunch of time on that, it was all worthwhile. But since I spent a bunch of time on that, we'll probably only get through section 5.1 of the book today, which is what we're scheduled for the syllabus anyway. And so first off, we've talked about chemical equations before, but I want to talk about some different parts of it, right? So if I was to write a chemical equation, we've seen this one before. Oxygen can combine with hydrogen to make water. This is the thing that when you see the picture of the space shuttle and you see all the flames coming out the back from the space shuttle part, not from the two boosters on the side, that big tank is filled with oxygen and hydrogen. I'm assuming liquid. I assume it's liquids of both of those, so they can put more in there. And then they're combined to make hydrogen. That's what all those flames are coming from. And when we do these chemical equations, we have to actually have everything balanced, the same number of atoms on each side. And we're going to talk about how to do all that, all right? But right now, I want to talk about just some nomenclature we're going to be using. And we've used this before. These are our reactants. So the reactants are whatever is on the left-hand side if somebody says reactants. These over here, this is products. In this case, maybe product. These subscripts here, these tell us how many atoms are in whatever molecule we're looking at. Each of these is a molecule. Okay, it's a molecule, or if we were doing, if it was ionic, it would be, let's say a compound. Okay, I'm going to say compound because it's more general. Tell how many of the atom to the left in the compound. Okay, so the same here and the same here. All these are compounds. We have more specific names for all of them. So this is a water molecule, which tells, when I say molecule, I mean it's not ionic. But this 2, best here, 2 means for every water there are 2 hydrogens. Okay? Over here, for every oxygen molecule, there are 2 oxygens. That makes sense? Okay. Then we have numbers out front. We're great for that. So these numbers out front, these are our coefficients. And they tell us how many, everything, you multiply them times everything to the right. Yes? Directly. Thank you. Yeah, my writing's atrocious. You should always ask that. Is that any better? I don't know. What was that? Tell how many of the atom directly to the left in the compound. Okay, and then coefficients. I'll repeat this after I write it. Coefficients. You're going to multiply these times the compound to the right. All right. So in other words, there are 2 hydrogen molecules, okay? Which means there are 2, each hydrogen molecule has 4 hydrogens in it, or sorry, each hydrogen molecule has 2 hydrogens in it, so I have 2 times 2 or 4 hydrogens. All right, so if we were to think about the number of atoms on each side of this equation, let's go ahead and do that in blue. I have 1 oxygen molecule, and there are 2 oxygens per oxygen molecule. So I have 2 oxygens. I have 2 hydrogen molecules. There are 2 hydrogens for each. So I have a hydrogen and a hydrogen and a hydrogen and a hydrogen. They're not bonded or anything. I'm just drawing hydrogens. Okay? On the other side, I have 2 water molecules. For each water molecule, there are 2 hydrogens, so I have 2 times 2 or 4 hydrogens. So I've got my 4 hydrogens again. And there's 1 oxygen per water molecule, so I have 2 oxygens. And this is a balanced equation, which is the main thing we're going to be working on today outside of this. This is messy. But if you look at this, we have the same number of atoms on each side of the reaction, right? All right, so there's a law that we use in chemistry. Okay, it gets more generalized in physics, but in chemistry, the rule is that matter cannot be created or destroyed in chemical reactions, which means we don't change any of the atoms. If I start out with 4 hydrogens and 2 oxygens, I have to end up with 4 hydrogens and 2 oxygens. If that makes sense. Okay, questions on what these things are in the equations before we move on to balancing equations? Okay. So, we can't destroy any of these atoms. All the atoms can do is switch partners in these reactions. And so let's say I had a reaction like, let's burn methane. So methane, this is natural gas. It comes out of your stove. It's mostly this. It's sort of a mix. And when I combine that with oxygen, I'm going to get carbon dioxide plus water. Now I need to make sure that I have the same number of atoms on each side of this equation. And so the way I do this, your book kind of has that just pick an atom and do it, and pick an atom and do it. And they kind of start with oxygen. And I would not start with oxygen usually, okay? It's not a hard and fast rule, but oxygen is usually present in multiple atoms or multiple molecules on each side, and it just makes it harder. So what I'm going to do for a set of rules here is pick an atom that is only present in one compound on each side of the equation. Let's go ahead and write this down as a rule. Or pick an element, I should say. Okay, and so what I'm going to do is I'm going to take my hydrogens here. I've got hydrogens in methane. I've got hydrogens in water, so I'm going to go ahead and balance that. I have 2 hydrogens on the right. I have 4 hydrogens on the left. So if I put a 2 in front of the water, all right, let me do that a different color. If I put a 2 in front of the water here, now I have 4 hydrogens. 2 times 2 for 4, I have 4 hydrogens. Those are balanced. Okay, then what I'm going to do is I'm going to repeat 1 until I can't do it anymore. I'm just going to keep picking things that are only present in on one side, things that are only in one compound on each side of the equation. Repeat number 1 until you can't do it anymore. And then balance the remaining elements. All right, so once you get to the end and you have to do something that's present more than one, then it will hopefully be pretty obvious, or it'll be a lot easier than it would have been earlier. So for this, I've still got oxygens and 2 sides on 2 on each side. So now I'm going to go do carbon, right? If I look here, I've got a carbon, 1 carbon on this side and 1 carbon on the other side. All right. We don't draw 1s in chemistry, but I'm gonna encourage you to draw your 1s, and then go back and rewrite the thing. Okay, at the end. Yes.
On the right side, isn't there 4 oxygen?
Did I miss something?
Because there's oxygen and H2O. And on the right?
On the right, there are 4 oxygens. Right. And I don't want to deal with that just yet.
Oh.
But that's correct. So I don't want to do the oxygens because they're in 2 different compounds and it's harder to balance. Okay, but I drew these ones, so now I fix these, right? I only have one number left to set, and then this is where that there are 4 oxygens is really important. I've got 1 times 2, so there's 4 oxygens here. I've got 2 times 1, so there's 2 oxygens here, 2 oxygens here. Everybody following that? Let's just write that one out. So I've got 2 oxygens. You guys agree with that? Okay, and over here I've got 2 times 0, so I've got 2 oxygens, which is going to give me 4 oxygens total. So I need to have 4 oxygens over on the left. If I put a 2 in front here, I've now got 4 oxygens, right? Whoops, I messed it up. All right, and then to make my chemistry professor happy, I'm going to rewrite it without the 1s. So this is one of those things where we actually have some format things we care about. Well, there's lots of things like that. But so that's my final balanced equation. I have the same number of atoms on each side of the equation. Okay? Matter was not created, nor was it destroyed. Questions? All right, let's try another one. Why don't you guys go ahead and do this one? We're going to go, this time we're going to do ethane. There's some ethane in the natural gas that comes out of your, sorry, that's not going to be any good. Why am I having trouble? 6. There we go. All right. Ethane. There's going to be some ethane in that natural gas. It's not the main component, but it will burn as well. Go ahead and try and balance that one. If you want help, I'm going to walk around real quick. If you want help, please call me over. Remember, you want to balance the easy ones first, which are almost never the oxygens. Balance of things that are present on one side at a time. Oh no, this is not important here. Wait. If you finish early, here's a nice challenge problem for you. Not that you wouldn't, I won't give you this one eventually, but at this point, that's the oxidation of glucose. That's the reaction your body does. Okay? I'm sorry, that should be an H12. Oh, goodness. No, that's really messed up. Let me fix my challenge problem. There, that's glucose. Yes, so put the 3 in front. Don't worry about what it does to the oxygens right now. It'll fix the oxygens later. Yeah, so you could do 7 halves, and I didn't realize I was doing that. So let's go ahead and look at this one right here. I see that I gave you a more challenging one than I wanted to, where I was thinking about. Let's go ahead and do this one, right? So if I look at this, what do you want to balance first? Hydrogens. Let's balance hydrogens first. So I'm going to go ahead and I've got 6 hydrogens on the left. I have 2 hydrogens on the right. If I put a 3 here, now I have 6 on both sides. All right, so which one should I do next now? Carbon, absolutely. So I've got 2 carbons on the left. If I put a 2 here, now I've got my carbons balanced. And now I need to count up my oxygens because that's what's left. If I do this, I have 4 oxygens, right? 2 times 2, and I have 3 oxygens. So 7 oxygens over here. This is where it was a little more difficult. This is like the next concept we worry about for this. So I'm going to need to have 7 oxygens on the left over here, and a way to do that is 7 halves, right? 2 times 7 halves is 2, right? You could put that in your calculator. 7 times 2 divided by 2 is 7, okay? Now, we can't have a 7 halves, or we can, but it's bad form. So what we need to do is fix that and not have any fractions here. And so we're going to multiply across everything times 2 to get rid of the 2 on the bottom. Does that make sense? So if I multiply this by 2, I get put a 2 there. Multiply 7 halves by 2 is equal to 7. So we'd end up with 7 C2H6 plus 7. So I'm going to multiply, let's just do this. Multiply times 2, multiply times 2, multiply by times 2, multiply times 2. So these equations are supposed to have these smallest whole number ratios. Multiply 2 times 2, I get 4. Multiply 2 times 3, I get 6. Okay? And what a good thing to do if you're doing this on a quiz or a test would be to check and make sure, check your work, okay? If I take 7 times, that's not a 7, that's a 2. This is, you guys need to like point out when I'm making these mistakes at the board this morning. I clearly haven't had enough caffeine yet. So I'm definitely gonna check my work now because I seem to be making mistakes, right? So what I'm gonna do here is, how many carbons do I have on the left side? Well, the only thing with carbons is my ethane. So 2 times 2, right? 2 ethanes, 2 carbons each ethane is gonna be 4 carbons. Let me do it in red. 4 carbons. Let me go to the other side. I've got 4 times carbon dioxide. 4 times 1 is 4 carbons. All right, so far so good. Now I've got 2 times 6 hydrogens, right? So 12 hydrogens. Okay, and if I go to the other side, I have 6 times 2 hydrogens. 12 hydrogens. Still good, okay? Oxygen is probably going to be the most complicated here, or it is, right? So if I really wanted to make sure I was short on time, I might just check my oxygens, because that's going to be the one most likely to be wrong. So if I have 6 times 1, that's 6 oxygens, right? Plus, I've got 4 times 2, that's going to be 8 oxygens for 14 oxygens on this side. I'll just write ox, it doesn't look like 140. So then over here, I've got 7 times 2, or 14 oxygens. Okay, and so all is right with the world. Eventually got that right. By checking, I definitely got it right. Yes?
Do you always divide by 2 and then times by 2, so different numbers if they're talking?
In terms, we're talking about for this?
Yeah.
So in terms of balancing it, in terms of doing my work to get there, I went and I knew I had 7 oxygens, a way to make 7 oxygens for O2. And we're going to see O2 a lot because it happens a lot in the air, it happens a lot in chemistry. 7 divided by 2 gives me, 7 divided by 2 times this 2, right, is going to give me 7. So the 2's cancel. That's one way you could do it. If you could look at it, figure out that you just need to multiply everything by 2. In the beginning, fine. That's fine as well. Did that answer your question? It's probably better if you get used to, since you're not used to doing a lot of these, that you get used to doing the divide by 2 to get your 7, and then you fix it.
Okay.
Questions? Okay. So we have this one that was a challenge problem, but I think what I'm going to do is I'm going to leave that by the top because there's really no new skills there. So we introduced the what do you do when you have a half skill. What I want to talk about is what do we do if we have polyatomic ions? Remember our polyatomic ions, right? Okay, so we have our polyatomic ions. Let's say we've got a reaction where, let's say I have calcium phosphate, okay, plus carbon plus chlorine gas, we'll get to that, plus calcium chloride, plus carbon monoxide, nasty, this is a nasty reaction, plus, I don't know what the name of this is, POCl3, but I could ask you to draw the shape and tell me whether it was polar. Questions? Nope, okay. So here's our reaction here, okay? It has a polyatomic ion in it. So what I want to remind you of when we look at that polyatomic ion, actually we're going to make that a challenge question. I had that down as a challenge question. Let's redo it. But let's talk about the polyatomic ion real quick. What does this 2 mean here? There's 2 phosphates, 2 of everything in the parentheses. How many oxygens are in this compound? 8, 2 times 4, right? What if there was a 2 here? How many oxygens would I have? 16. 2 times 4 times 2, okay? But let's start with an easier polyatomic equation. So we've got chromium nitrate, okay? Challenge while I'm writing it out. What's the charge on chromium? You know it based on the compound I just wrote. 2 plus, very good. And then I've got a potassium nitrate over here and a chromium hydroxide. Okay. This is better. This is easier. Okay. All right. So the thing we want to keep in mind here, and that's going to make this easier, is that these nitrates, that nitrate is a nitrate. It stays together. Okay, it didn't stay together up here, which is why that was a more complicated one. But here, this nitrate stays together. So we see the nitrate over here again, right? So we can think about all those together and make it a little bit easier to balance. And then if we've got a hydroxide here, the hydroxide stayed together over there. Do you see that? You have OHs on each side. So we can keep those together while doing this, and it might be a little bit easier to balance. But let's go ahead and do our balancing process. So what's something that's on each side of the equation only once? Chromium, right? Okay. So what I can do is I'm going to put a 1 in front of this chromium and a 1 in front of that chromium. There's 1 chromium here, right? And 1 chromium there. I'm just going to put the 1s in and I'll rewrite it when I'm done. Okay, well, what else could I do here? I could do those potassiums, and I'm going to end up in trouble, aren't I? By our method, right? If I put a 1 here and a 1 here, is it going to be okay? It's not. So let's pick one of those polyatomic ions to make sure it ends up okay. So how many? I've got this 1 fixed, right? Okay. So if I take this 1 fixed, I've got, how many nitrates do I have?
2.
2. How many nitrates over here? 1. So let's put a 2 in and see if that saves us. Okay. So in addition to picking one thing, I also like to bounce back and forth based on what I've got there. And in terms of once I fix something, balance something related to it. So we've got this 2 potassium. I now have 2 potassium nitrates. I have 2 potassiums. I'm going to have 2 potassiums. Let's go ahead and put the 2 over there. And then let's see if it worked. All right. And now we're just going to, let's count up atoms. Let's count up atoms and make sure we've got it right. So I've got 1 chromium over here. How many chromiums do I have on the other side? 1 chromium, good, okay. I've got how many nitrogens on the left-hand side? 2, okay. Parentheses, 2 nitrogens, 6 oxygens, okay. So I'm going to have 2 nitrogens on the left-hand side or the reactant side. How many nitrogens on the product side? 2 nitrogens, okay. So we're going to do 2 nitrogens there. Let's see, how many potassiums on the left-hand side? 2 potassiums, right? And 2 potassiums on the right-hand side. Do you see that? And then oxygens, always the troublemaker. How many oxygens over here? I have 2 times 3 for 6 oxygens in this compound, plus I have 2 times 1, right? Okay, plus 2 oxygens here to give me 8. I'm going to write ox so we don't think it's 80. And then over here, I have 2 times 3 for 6 oxygens, and I have 1 times, I've got 1 oxygen here, but there's 2 of these hydroxides, right? So I have 2 oxygens over here. So 8 oxygens on both sides. So that was good. Questions? That was a lot. All right, so we've got lots of things going on. You're going to want to practice this because we've got subscripts and then we have subscripts of subscripts, right? We have to multiply these, then we might have a number out here we have to multiply by, which we didn't here. But so we have a lot going on here in terms of the balancing and making sure everything works out. Let's try. Let's try another one. I'm going to give you one without polyatomic ions. And I'm going to sit here and think of a good one with polyatomic ions. All right, how about balancing that? Silver sulfide reacts with oxygen to make silver oxide and sulfur dioxide. And here's the next one we're going to work underneath if you finish the one I've got up there. Please call me over with any questions.
because I was going to make that. Right. This must be it's also two solvers, you have five over here, right? And here you had 3 times that. You did. No, 6 or 6. Like I said, if you finish the first one, go on to the next one. Knock them both out. Nice job.
All right, let's go ahead and do this one, and then I'm actually going to work down to this one as well. And then I'm going to hand back your exams. So you're going to need to practice these. I'm going to do a mess of practice problems in the back of your book. And I recommend that you, if you feel like you don't have them after you get your practice problems, which are your homework, that you do more. You've got lots of problems in the back of your book that are in the odd problems that have answers and worked answers. So this one right here, I've got, let's balance the silvers. How many silvers do I have on the left-hand side, AG? 2. How many on the right-hand side? 2. They're in one column, okay? So now I've fixed the number of sulfurs, right? So let's do the sulfurs next. So I have how many sulfurs on this side? 1. How many sulfurs on this side? 1. Great. All right, and now we do the oxygens, which are always the most challenging, right? How many oxygens on, well, either side, we're gonna do we have to do the right-hand side here. So left-hand side, we haven't determined them yet. How many sulfurs over here? Oxygens, I'm sorry. How many oxygens? 3 oxygens, right? 3 oxygens. So I need 3 oxygens on the left-hand side. How do I do that? I do 3 halves. Okay, 3 halves times 2 is 3. And so now I just need to multiply everything by 2 to make my chemistry professor happy. So I'm going to do 2 of these. Multiply 3 halves times 2 is 3 of these. Multiply that times 2, 2 of these. Okay, plus 2 of these. Is that what other people got? I am not, since I'm running out of time here, I'm not going to check it, but I recommend you check it. Okay, and once again, if I was short on time, what I would do, I would just check the oxygens because they're most complicated. If there's a problem with the oxygens, there's a problem. Let's try this one down here. Okay, so here we have a mess of polyatomic ions, and we have some atoms here, but let's go ahead and try those. So calcium, first thing I see, right? I've got calcium in one compound on each side of the equation. How many calciums on the left-hand side? 3. How many calciums on the right-hand side? 1. So I'll put a 3 in front. Okay. Now I've fixed how many nitrates I have, right? How many nitrates do I have? 6, right? So here we go. 3 times, this is my nitrate, 3, I've got 6 of these. How many nitrates over here? 2, right? 2 times my nitrates. So I'll need to put a 3 in there in front of there to fix it. Okay, actually I'm going to put a 1 here in front of my calcium just to remind myself I've already done that one. All right, so now what did we do? We did nitrates, right? So we have magnesiums. How many magnesiums over here? 3. How many magnesiums here? 3. So I'll put that 1 to remind myself I'm done. Okay, and if I had a pencil, if I had a pen, I only work with pens because I'm used to working with lab books. But if I had a pencil, I could just erase those two and I'm done. Okay, those are balanced, same number of atoms of each type on each side. And I could check that more carefully. I'm going to go ahead and hand these back. So in terms of the test, if you were, and you've seen your midterm grades at this point, what I'm going to say is if you're not super happy with how your things are going in this class, I recommend you do more homework, not homework, more practice problems. Okay, so I assign homework, but if that's not enough, what you need to do is you need to practice more problems. There are lots of problems in the back of your book. Remember, I'm available from 1 to 5. Today I'm available from 1 to 5. I'm available from 1 to 5 most days, most Monday and Wednesdays. So feel free to take advantage of that time. Feel free to take advantage of subject tutoring. Once you have your exam, if you don't have anything you want to talk to me about, you're welcome to get up and leave. You don't have to wait until everything's done.
Dr. John,
Yes.
are you still available from 1 to 1:30?
Yes, absolutely.